In this tape we're going to be concerned with graphing of continuous functions. But before we get to that subject, and in preliminary to being able to see what happens with continuous functions, we want several theorems which are called mean value theorems. These are called mean value theorems because they assert the existence of an intermediate value between two numbers, usually a and b, the endpoints of a given interval, and at the intermediate value a certain thing happens. The first of these theorems is the mean value theorem for continuous functions. All of these theorems have got uses not only for graphing but also for other theoretical things involved with calculus. The mean value theorem for continuous functions states the following. If f of x is continuous on closed interval AB and C is some number between f of A and f of B, then there is a point Z in the interval AB so that the value of f at Z is equal to C. So it asserts that there's a number Z between A and B so that f of Z is C. Moreover, it asserts that a continuous function on a closed interval, or for that matter an open interval, takes on all the intermediate values between any two values that are taken on. Picture something like this. This is the interval AB, and let's say, for purposes of illustration, this is f of A, and this up here is f of B, and C is any number here between the two. Then there has to be some number Z between A and B so that the value of f at Z is exactly equal to C. All right. To see that this is the case, we're going to follow through a brief proof that it is. Let's suppose f continuous on AB and C between f of A and f of B. Right? Without any real loss, you were going to suppose that f of A is smaller than f of B. The other situation is similar. So let's suppose that f of A is less than f of B, and let's let Z be equal to the supremum, or least upper bound, of the set of all x such that if t is in a to x, then f of t is less than C. Okay? Z is going to be our candidate for the point that maps on to C. All of these other points here between A and Z, there's an interval. The interval from A to any point prior to here goes into f of A to C. Okay? So let's look at the situation. We're going to show that f of Z is equal to C. In order to do that, what we're going to really do is we're going to show that it can't be less than C and it can't be greater than C. So suppose f of z was less than C. Right? We have a picture that looks something like this. Here's C and z, and f of z is some value less than C. Right? But then since f is continuous, there would be a delta so that f of t is less than C if t is in the interval between z minus delta and z plus delta. So all of these values here on this entire interval would have to be less than C. And this would mean that z was not the supremum. So this can't happen. So it's not possible that f of z be less than C. Suppose now, on the other hand, now that f of z was greater than C. Well, then we would have f of z here. Draw it again here. Here's C. Here's z. F of z would be strictly greater than C. If f of z is greater than C, though, again, there is a delta greater than 0, so that f of t is greater than C in the interval that consists of t between z minus delta and z plus delta. So that all of these values here would have to map to something larger than C. But that's not possible because Z supposedly was the least upper bound of all the numbers, and these numbers back here are not numbers for which f of t is less than C for all smaller t. So this can't happen. So the only thing that can happen is that f of z be C. And so what we have done then is, assuming that we take a number C between f of A and f of B, we have been able to find the number Z, namely the supremum of this set of X, the least upper bound of it, so that the value of the function at that number Z is C. Consequently, every number in between f of A and f of B is taken on by some number between A and B. Now this is intuitively what you think of when you think of a continuous function. Especially if it's a nice smooth function, it goes from f of A to B f of B, its graph does. All right, the next result we want is kind of a mean value theorem too. It's called Rolle's theorem. It's generally considered to be intermediate, or lead up to the mean value theorem for differentiable functions. But Rolle's theorem asserts the following. If f of x is continuous on closed interval AB and differentiable on the open interval AB, then if f of B is the same as f of A, there is a point Z in the open interval AB and z has a derivative of 0. F has a derivative of 0 at z. Picture is something like this. Here's a, b, and f of a is the same as f of b. Then there has to be some point z between them so that the derivative at z is 0. Providing the value of the function at a and the value of the function at b are the same. All right. To prove this, you basically look at three possible cases. One is sort of a silly case perhaps, but suppose f is identically constant on the interval ab. Well then, the derivative at every point in ab is 0, so choose any point z in the open interval AB. And f prime of z is going to be equal to 0. The second case is, suppose there is a point x naught in AB so that f at x naught is larger than f at a. All right? So that might be this case right here if there was a point x naught and the value at x naught was larger than it is at a. Then f takes on its maximum on the interval AB at some point z. Right? There is a z so that f is maximal at z on the interval AB. Right? But this point z can't be one of the two endpoints. And we know that it has, one of three things has to happen. It either is one of the two endpoints, or it's a point where the derivative doesn't exist, or the derivative is equal to 0. Well, since it can't be the endpoints, and once it's not the endpoints, the derivative exists on the entire interval AB, it must be a point where the derivative is 0. So if this second case happens here, then the derivative at that point is 0. Third case is this. If there is x naught in the interval a to b, open interval, so that f of x naught is less than f of a. Picture like so. A, b, f of a, which is equal to f of b, and there's a point x naught here, so that the value of the function at x naught is less than it is at f of a. Well then, there's a point z in the open interval AB. Well, it will eventually be in the open interval AB, but so that f is minimal at z on the closed interval a to b. All right. Then again what happens is this. Z, say it's right here, cannot be either a or b because the function isn't minimal at a or b. There's a point x naught where it's smaller. So z has to be some point in the open interval AB. And also, since the function is differentiable on the open interval AB, the derivative at z must exist. And since there are only three possibilities, z is the endpoint, or it's the place where the derivative doesn't exist, it must be that the derivative is equal to 0. That's the only third possibility. So the derivative at z must equal 0. Now let's look at what we've got here. Right? The claim is that one of these three cases must occur. If the function is not constant on the interval AB, a function whose value at a is the same as the value at b, then there must either be an x naught where the function is larger at x naught than it is at a, or there must be an x naught so that the function is smaller than it is at a, because if there were no x naught where it was larger and no x naught where it was smaller, then the function would have to be identically constant on the interval AB. So one of these three has got to occur, and in either one of these cases, you can find the number z. In this case, choose any z. In this case, choose a z where the function is maximal. In this case, choose a z where the function is minimal. So you can always find the point z in the open interval AB so that the derivative of f at z is equal to 0. All right, now we want to get to what's called the mean value theorem, or the mean value theorem for differentiable functions. So frequently it's just called the mean value theorem. The mean value theorem states the following. If f of x is continuous on the closed interval a, b, and is differentiable on the open interval AB, then there is a point Z in the open interval AB so that f of B minus f of A over B minus A is equal to the derivative of f at the point Z. The picture looks something like this. If here's A and here's B, f of A and f of B, then there must be some point Z, say here, so the derivative of f at Z, the slope of the tangent line at Z, is the slope of this line connecting AF of A to BF of B. Right. Here's how to see this. We basically take the function f of x and we subtract the function which goes through the origin and has a slope f of b minus f of a over b minus a. That's to say, let g of x equal f of x minus f of b minus f of a over b minus a times x. Right. Then, the claim is that when you do this, it's almost apparent that when you do this, that the resulting difference is going to have the same value at A as it has at B. That's to say, g of A will be equal to g of B. Let's check that. G of A. Well, that's f of A minus f of B minus f of A over b minus a times A, which is equals to, if I put all of this over b minus a, I get f of a times b minus f of a times a plus, no, minus a times f of b, so minus f of b times a, and plus f of a times a. All right. Now, here, these two here, f of a and minus f of a can be removed from this because one is the negative of the other. So we end up with f of AB minus f of BA. How about g of B? Well, it's going to be equal to f of B minus, we just put B in for x, f of B minus f of A over B minus A times B, which is going to be equals to, bring this all over B minus A, What have we got? We got f of b times b minus f of b times a minus f of b times b and plus f of a times b. Right? Now here, this right here and this are the negative of each other, and so the result is f of a times b minus f of b times a. Well, that should be the same as what we had here. We have f of a times b minus f of b times a. So it follows that g of a is equal to g of b. Right? But now g is continuous on the closed interval and differentiable on the open interval, and its value at the two endpoints are the same, so that Rolle's theorem applies to this. Right? That's to say, there is a z in the open interval AB, so that g prime at z is equal to 0. But what is g prime of z? It's f prime of z, differentiating this. And now this is just a constant multiple of x, so the derivative of this is going to be the constant. So it's going to be minus f of b minus f of a over b minus a. So what do we have? We have that 0 is f prime of z minus f of b minus f of a over b minus a. So consequently, f prime of z is f of b minus f of a over b minus a. And so that z is the point in the interval where the derivative at that point takes on the slope that you get between the 2 points, af of a and bf of b. Right? You can see this is also a particular case of Rolle's theorem. In the event that f of a is equal to f of b, then f of b minus f of a will be 0, and there will be this point z in between where the tangent is flat. That's to say where the derivative is equal to 0. Now I want to look at the properties of functions defined on an entire line or on an interval. And in particular, we want to talk about when a function is increasing or decreasing. That's to say whether when it goes up as x increases or when it goes down as x increases. Definitions are as follows. F of x is said to be increasing. Now there are really two terminologies involved here. Some people use the word increasing. Some people use the word strictly increasing. I'll abbreviate the STR, increasing. If whenever x1 is less than x2, then f of x1 is less than f of x2. All right. It's said to be non-decreasing and the people that use the alternative terminology sometimes call this increasing if when x1 is less than x2, then f of x1 is always less than or equals to f of x2. Now, these terminologies are changing to some extent, but you can always get things straight if there's any ambiguity by using strictly increasing to mean that the value at x1 is strictly less than the value at x2, or to use non-decreasing when you want to allow for the possibility of equality. Right? This means, of course, that the function is going up as x increases, and this one here means that it's going up or maybe flat as x increases. f of x is said to be decreasing, or the alternative terminology is strictly decreasing, if when x1 is less than x2, then f of x1 is greater than the value of f at x2. And it's said to be non-increasing. Or in the alternative technology, decreasing. If when x1 is less than x2, then f of x1 is greater than or equal to perhaps f of x2. Again, if you use the word strictly decreasing and non-increasing anytime when there might be some ambiguity, then you won't have that ambiguity. Because no one uses these any differently. Okay, now for graphing functions, we're going to want to know where the function is increasing and where it's decreasing. So these same definitions hold on a closed interval AB or on an open interval AB, with the restriction that x1 and x2 must come from the interval AB. Right? And now what happens is, if on an open interval AB, if the derivative of f is greater than 0, then f is strictly increasing on that interval. Right? This is somewhat intuitive. If the derivative is greater than 0, then the slope of the tangent line is positive, and so you expect the function to be heading upward. Proof of this is as follows, though. The proof is by contradiction, and the idea is to suppose that it's possible that this not holds, that we have an interval AB, and we have 2 points, x1 and x2 in this interval, so that f of x1 is greater than or equal to f of x2, maybe equal. Right? Well, if x1 is less than x2, and f of x1 is greater than or equal to f of x2, we want to show that this can't happen. Since x1 is less than x2, we're going to apply the mean value theorem here. There is a z between x1 and x2. That's to say in the interval x1, x2, so that the derivative at z is equal to f of x2 minus f of x1 divided by x2 minus x1. But f of x1 is larger than f of x2, and x2 is larger than x1, so that says that this is less than or equal to 0. But f prime of z supposedly was greater than 0, and so it's not possible that this happened. This is not possible, and so it must be that for any 2 points, x1 and x2, in the interval, f of x1 is less than f of x2, and f is strictly increasing on the interval. Right? So here's one result here. The other analogous ones also hold. That's to say, if f prime of x is greater than or equal to 0 on AB, then f is non-decreasing on AB. The reverse results for strictly decreasing it and non-increasing functions hold here. That's to say, if f prime of x is less than 0 on AB, then the function must be heading downward. Then f is strictly decreasing on AB. Right? If it's strictly less than 0, then it's strictly decreasing. And fourthly here, if f prime of x is less than or equal to 0 on AB, then f is non-increasing on the interval AB. Now this is going to be quite useful for graphing, because what you're going to want to do is this. You're going to take a look at a function f of x. It's a reasonably nice function. It's differentiable. You find the derivative. You find out where the derivative is equal to 0 and where the derivative is greater and less than 0. On intervals where the derivative is greater than 0, the function is going to be increasing. Where it's less than 0, it's going to be decreasing. And so this will help you in graphing. It's not going to change at all between points on those intervals. It's monotonicity. And if it's any one of these four here, it's said to be monotone, and that's the reason for the having monotone functions here. All right, we want to look now at a relatively simple example. Involves finding the places where a function is increasing or is decreasing, those intervals. And for this purpose, let's look at the function f of x equals to x cubed minus 3x plus 1. And the basic idea is that we wish to plot the graph of this function. All right. And easy points to plot. If we were listing points x, y on the graph, an easy points to plot would be when x is equal to 0, because then the function is 1. So at 0, the value of the function is 1. Now, it's going to turn out that when you plot points for determining the graph of a function, you don't just wish to do like you perhaps did earlier and plot just a number of points and connect the dots with them. What you want to do is you want to find appropriate points that will indicate how the function behaves and plot those points. So let's look at the derivative of this function. F prime of x is equal to 3x squared minus 3, which is equal to 3 times x minus 1 times x plus 1. All right. So that f prime of x is 0 if x is equal to 1 or minus 1, and f prime of x is greater than 0. F prime of x here is relatively simple. Its graph is a parabola opening up, and so it's going to be greater than 0 if x is larger than 1 or x is less than minus 1, and f prime of x will be less than 0 if x is between 1 and minus 1. So 1 and minus 1 are two reasonable points to plot here. This was a relatively simple function, but in general, wherever the derivative is equal to 0, even if those points are not particularly neat, it's worthwhile plotting them. Okay? What? The value of the function at 1 is 1 minus 3 plus 1, or minus 1. The value of the function at minus 1 is minus 1 plus 3 plus 1. 3 and 1 is 4, minus 1 is 3. So at minus 1, the value of the function is 3, and at 1, the value of the function is minus 1. All right. Now, what we also know is that the function over here, the function is increasing. And then between minus 1 and 1, the function is decreasing. And between 1 and on out, the function is increasing. Right? So let's plot just a couple more points here, and then we know that we're done, pretty much, because the function is going to increase till it gets up to here. It's got a derivative of 0 here, and then it decreases till it gets down to here, and then it increases. So the function at, let's say, 2 is 8 minus 6 is 2, and 1 is 3. So the value of the function of 2 is 3. So the function is up here at 2. And now, by the mean value theorem, you know that it takes on all the values in between here, and the graph looks something like this. The graph then looks something like this over here. And let's look at the value of the function at minus 2 as a sort of a final point here. F of minus 2 is minus 8 plus 6 is minus 2 plus 1 is minus 1. So the value of the function at minus 2 is minus 1. It takes on all values in between here. Consequently, it goes through 0 somewhere in between here. It's not easy to tell where, but it does. And the function is increasing, so it gets to this point, then decreasing, and then increasing. And so you know that the function is not going to do anything tricky outside of here, not anything particularly tricky. And so by drawing the graph on this interval, we know that what the function is going to look like on the entire real line. It's going to be larger and larger over here, and smaller and smaller, more and more negative over on this side. So this is an indication then of how you can use the derivative to determine where the function is increasing or decreasing. We want to look at what's called relative maxima and minima for a particular function. Right? A point x naught is called a relative maximum for function f if there is an interval a b on which f is defined, let's say in the domain of f, so that x naught is in AB, the open interval, and x naught is the maximum of f on the closed interval AB. This is a little confusing sometimes because the point x naught is frequently called the maximum, although actually it's the function which takes on its maximum at x naught. Right? So what must happen is that there must be some interval on which x naught is the maximum, however small this interval might be. Similar thing here is for the minimum. That's to say, a point x naught is called a relative minimum for f of x naught if there's an interval AB in the domain of f, so that x naught is in the interval, open interval AB, and x naught is the minimum instead of maximum of f on the interval AB. Picture is something like this. If this is the graph of f of x, then this right here is a maximum. This should look more like this if this is going to be a function. This is a relative maximum. Here's a relative minimum, and here is a relative minimum. If there was a little peak like so, then this would be a relative maximum, and there would be a relative minimum. Right? All that's required is that there be a small interval on which the function takes its maximum at that point. Right? These are sometimes called strict relative maxima and strict relative minima because they actually would have a relative maximum or minimum if there were ties. Here, in this picture here, there are no ties on the interval, and it's a strict maximum or a strict minimum on that interval. Okay, so relative maxima, like so. Right? This is definitely not an absolute maximum or a maximum because there are points over here where the function is larger. But there is a small interval here on which it's the maximum value. Similarly, relative minima here, and here, and here. Right. At any point where the function takes on its relative maximum or minimum, it must be that one of two things happens. Either the derivative is equal to 0 or the derivative does not exist. Such points where the derivative is equal to 0 or the derivative does not exist are called critical points. So that x0 is a critical point for f if the derivative at x0 is equal to 0 or the derivative at x0 does not exist, does not have a derivative. Right? Now these are the points where you should look if you want to find relative maximum and minimum, and one way to determine whether or not you've got a relative maximum or minimum, if the function is differentiable, is to determine whether it's increasing to the left of the point and decreasing to the right. If it's increasing to the left and decreasing to the right, then it's going to be a relative maxima. If it's decreasing to the left and increasing to the right, then you're going to have a relative minima. So the way to check for these things is here to check the derivative, find the places where the derivative doesn't exist, or where it's equal to 0, right? And check to the right and to the left of those to see whether the function is increasing and then decreasing, in which case you've got a relative maximum, or decreasing and then increasing, in which case you've got a relative minimum. All right, what I'm going to do next is a relatively simple example which illustrates relative maxima and minima. Examples are not generally that easy to work. But let's look at the function f of x is equal to x to the 4th minus 2x squared. The derivative of this function is 4x cubed minus 4x, which is equal to 4 times x times x minus 1 times x plus 1. The example was made up so that there would be relatively easy places to check where the derivative is equal to 0. Particularly the derivative of x is equal to 0 if x is equal to 0 minus 1 or 1. Right? So if we're trying to graph this function, those are points that we should be looking at. The value of the function at 0 is 0. The value of the function at 1 is minus 1. So x and y at 0 is 0. At 1 it's minus 1. At minus 1, the value of the function is also minus 1. You can see that easily here without much checking because this function is an even function. That's to say the value at x is the same as the value at minus x. Right? So we've plotted 3 points at this time. Now, what we want to know really here is where is the derivative positive and where is it negative? So if here's 0 and here's 1 and here's minus 1, since the derivative is a continuous function, in order to determine where it's positive and where it's negative, all we need to do is check a point in between. If it's positive at that point in between 0 and 1, and it cannot be negative at any other point, because if it were, it would have to go through 0, and it doesn't. These are the only places where the derivative is 0. So, in particular, if we check the derivative at a half, we find that this is positive, this is negative, and this is positive, so the derivative is negative, and so the derivative is going to have to be negative on this entire interval. If we check the derivative at minus a half, we find that this is negative, and this is negative, and this is positive, and so that the resulting thing is positive, and so the derivative has to be positive on the interval from minus 1 to 0. We check the derivative at 10, we find that all three of these are positive, and so that the derivative has to be positive over here. And if we check it at minus 10, we find all three are negative, so the derivative has to be negative. It's the product of three negative quantities over here. So really only checking at one point in between where the derivative is 0 will suffice to determine whether the derivative is positive or negative, if providing the derivative is continuous. That's by the mean value theorem. Okay, so what do we know then? We know that the function is decreasing, then increasing, then decreasing, and then increasing. Let's plot a couple of more points. Again, I'm going to mention that this is a particularly simple function to graph for the purposes of illustration. Divide the function at 2 is, 16 minus 8, or 8. So the value of the function at 2 is 8. So the function is increasing, and so it looks like this. This is a relative minimum. This is a relative maximum. This is a relative minimum. The value of the function at 2 was 8, and since the function is even, the value at minus 2 is going to be 8 also. And so the function is going to go through 0 somewhere between here and here. That's not necessarily easy to determine. And the graph of the function looks something like this. Relative minimum, relative maximum, relative minimum. These two are both absolute minimums, but there's no absolute maximum to this function. The function is decreasing, then increasing, then decreasing, and then increasing. And we've got a good idea then of the graph here of the function. We now want to add some descriptive terms here for graphing functions, and these are going to involve concavity. A function f of x on, let's say, the interval, closed interval AB, is concave upward, or just concave up, if all secant lines lie above the graph. Pictures like this. This is the interval AB. The function is going to be concave up. That's to say it's going to have a concavity on the upward side if whenever you take a line connecting 2 points, x1 and x2, all the points on the line between x1 and x2 lie above the graph of the function. For any of these lines, connecting any 2 points, x1 and x2, you must have the secant lines lying above the graph. All right? Now, sometimes it's allowable. You could talk about strictly concave up. Well, most things will tend to be strictly concave up. If they're strictly above, and it's allowable sometimes to have them touch the graph. And however, we don't really need to make much distinction here. All right, now if f of x is differentiable, right, then and concave up, then all the tangent lines lie below the graph. That's to say, all of these tangent lines here to the graph of the function lie below the graph. The function happens to be differentiable and it's concave up. Right? And that's if and only if. That's to say, if it's differentiable and all the tangent lines lie below, then all the secant lines will have to lie above. That takes quite a bit to prove this. It's not particularly straightforward, but and I'm not going to go into it here, but it's almost visually evident that all of the tangent lines here are going to lie below the graph if the function is concave up. And moreover, if they do lie below the graph, then the function is going to be concave up. Concave up, you can think of as going in this fashion right here. And this also holds true if, let me make this if and only if, because it's true if and only if. Well, if f is x, if f is differentiable, then the tangent lines lie below the graph. If and only if it's the secant lines lie above. And if f is differentiable, then the tangent lines lie below the graph, if and only if the derivative is increasing. So for differentiable functions, these two statements here are equivalent to the statement that it's concave up, or that all the secant lines lie below the graph. You can see here that the derivative for this particular one that I've drawn is increasing. It starts here negative, and it gets less negative, and it gets positive, and the derivative is increasing. So the shape of a function which is concave up is something like this. The second thing that you can note here is this, that concave up doesn't have much to do with increasing or decreasing. That's to say, here this function is decreasing on this interval, but it's concave up. And it's increasing on this interval, and it's also concave up. So you can have a function which is decreasing in concave up, or a function which is increasing in concave up on an interval. However, once you know the concavity, that it's concave up, then you can, that's going to be an aid in graphing the function. Right? F of x is said to be concave down on AB if the secant lines lie below the graph. Picture is something like this then. This function here is concave down on the interval a, b. All the secant lines lie below the graph. And you might guess, of course, that if a function is concave down, then the negative of the function is concave up. And also that this is going to hold, right, analogous to this, if f is differentiable, all tangent lines must lie above. So the tangent lines must lie above the graph like so. And the derivative is decreasing. If it's differentiable, the derivative is going to be decreasing. The derivative starts out positive here, it gets less positive and becomes negative over here like so. And again, here, this function on the left-hand part here is increasing in concave down. Here it's decreasing in concave down. So you can have increasing in concave down, and you can also have decreasing in concave down. So that these are not strictly related in any ways to increasing and decreasing. You can have any one of these four combinations. Now, the situation is this. In order to determine when the function is concave up, we want to know when the derivative is increasing, because that will make these other things happen here too. And to determine when the derivative is increasing, if the function is nice enough, you check the second derivative and see whether it is greater than 0, because this will imply that the derivative is increasing. To see where the derivative is decreasing, you check the second derivative and see where it is less than 0, because this will imply that the derivative is decreasing. So, on any interval where the second derivative is greater than 0, the function will be concave up. And the second derivative less than 0, the function will be concave down. So the second derivative is the key to determining where a function is concave up or concave down. Right? So constantly when we graph a function, we're not only going to want to look at easy points to plot and where the function is increasing or decreasing, that's to say where the derivative is positive. We're also going to want to take the second derivative of the function and determine when it's the derivative of the derivative and determine when it is positive and when it's negative and when it's equal to 0. Right? If you have got a differentiable function that's concave up on one side of a point and concave down on the other side, or vice versa, concave down and then concave up, the point where the function changes concavity is called an inflection point. Such as one of these two here. Right? Now, some authors will allow the function not to be differentiable in order for there to be an inflection point. It just needs to change concavity. Some will insist that it has to be continuous. But a reasonable definition is that if the function is differentiable and changes concavity, then that's called an inflection point. The place to look for inflection points are places where the second derivative is equal to 0. And to check then whether or not the derivative the second derivative is positive on the right of the point and negative on the left, in which case you will have an inflection point, or vice versa. It's not just enough, however, to check places where the second derivative is equal to 0, because these may not be inflection points. Just like it's not enough to check places where the derivative of a function is equal to 0 to find relative maxima and minima. A function does not have to have a relative maxima or minima just because the derivative is 0. A function may simply be flat there, such as the function x cubed at 0. The derivative is 0. It's not a relative maxima or minima. X to the fourth at 0 has a second derivative which is equal to 0, but 0 is not an inflection point. The function is strictly concave up. X to the fourth is. So, concave up, concave down, and inflection points. Okay, let's take a look at a couple of examples here. Again, these are relatively simple examples to illustrate the point. So let's look at f of x equals to, let's say, x cubed plus 3x squared plus 3x minus 2. All right. If we wish to graph this, clearly there are some simple points to plot. The value of the function at 0 is minus 2. The value of the function at 1, for example, is 7 minus 2 is 5. Huh? The value of the function at 1 is 5. Right. That's not telling us very much at this point. We want to take a look at the derivative of the function, and again, this function has been made up so that it's relatively simple. So the derivative is going to be 3x squared plus 6x plus 3, which is equal to 3 times x plus 1 quantity squared. So the derivative is always going to be greater than or equal to 0, and so this is always greater than or equal to 0, so that this particular function is strictly increasing. There's only one point where the derivative is equal to 0, and in the case where you just have one point where the derivative is 0 and the rest is positive, the function is flat at that point, and then it's increasing after that. The derivative is equal to 0 at x equals minus 1, and the value of the function at minus 1 is going to be minus 1, and 3 is 2. Minus 3 is minus 1, minus 2 is minus 3. So the value of the function at minus 1 is minus 3. The derivative is flat at this point. Okay? Let's look at the second derivative. It's going to be equal to 6x plus 6. Or 6 times x plus 1. And this is equal to 0. Second derivative is equal to 0 when x is minus 1. And it's greater than 0 when x is greater than minus 1. And it's less than 0 when x is less than minus 1. So, consequently, the function is going to be concave up when x is greater than minus 1 and concave down when x is less than minus 1. Right? Minus 1 is going to be an inflection point. The function is always increasing, and it looks something like this. It's concave up over here and concave down over here. Inflection point at minus 1. Let's look at another example. Let's look at f of x equals x cubed minus 3x. The derivative then of f, again this is a simple example, is 3x squared minus 3, which is 3 times x minus 1 times x plus 1. And the second derivative of x is equal to 6x. So that this is greater than 0 when x is greater than 0, and it's less than 0 when x is less than 0. The second derivative is. So the math of this function is going to be concave upwards to the right of 0, concave downwards to the left of 0. The easy point to plot is that the function is 0 at 0. Right. The derivative is 0 at 1 and minus 1, so it's worthwhile plotting those points on the function. The value of the function at 1 is minus 2. The value of the function at minus 1 is 2. Actually, this is an odd function. That's to say the value at x is the negative of the value at minus x, and so this function is going to be symmetric about the origin, making it relatively easy to plot. The value of the function at 2, for example, is 8 minus 6, or 2. And the function at minus 2 is minus 2, and the graph of this function then looks like this. The function is concave up over here. It's concave down over here. It's increasing, so it gets to minus 1, then it's decreasing, and then it's increasing. Concave up to the right of 0, concave down to the left of 0. Right? Well, this is a very relatively simple example. It illustrates what you need to do. Namely, when you're trying to graph a function, take the derivative, find where it's equal to 0, find where it's greater than 0, find where it's less than 0. That's where the function is going to be respectively increasing and decreasing. Take the second derivative, find where it's greater than 0, equal to 0, and less than 0. Where it's less than 0, the function is going to be concave down. Where it's greater than 0, it's going to be concave up. Where it's equal to 0, these are places where it may change concavity. If it does, those are going to be inflection points. 0 here, for example, is an inflection point for this particular function. So here we have two examples of functions that illustrate possible things that can happen with respect to concavity. Okay, in graphing the functions, it's particularly useful to look also at points where the function is not defined, and to determine what happens when x gets close to that point, and also to look at large values and large negative values, small values if you want, and see what happens to the function as x gets large, or when it gets large in absolute value but negative. For this purpose, we want to look at limits again and note the following definition. The limit as x approaches a from the right of f of x, right, will be said to be infinity if for every number m there is a delta greater than 0 so that f of x is larger than m if 0 is less than x minus a is less than delta. Here x, there's no absolute values around the x minus a, so x minus a is going to be greater than 0. That's the x is going to be larger than a, and x minus a will be less than delta. And no matter how large a number m you choose, you have to be able to find such a delta so that the function is larger than m. An example of such a function, fairly simple, is y equals 1 over x. At 0, the graph of this function looks like this. The limit is plus infinity on the right. The rest of the graph looks something like this. Right. Conversely, the limit is going to be minus infinity if for every m now however negative m happens to be, there's a delta so that f of x is less than m when 0 is less than x minus a is less than delta. Now this is on the right. The limit as x approaches a on the left, and sometimes this is also written with a downward arrow. That's to say, sometimes this is written as limit as x on the left increases to a, and this one is written as the limit as x decreases to a. So you might note that this notation occurs sometimes. Anyway, the limit as x approaches a on the left, with the minus sign here, of f of x is equals to infinity if for every m there is a delta greater than 0 so that f of x is larger than m when 0 is less than a minus x is less than delta. Here x is to the left of a, x is less than a, and this difference between a and x is less than delta. So that, for example, here at 0, 1 over x approaches minus infinity. If you want the function to be less than some number m, you simply need to choose delta small enough and stay to the left of 0 by something less than delta. Okay, so here are the limits from the right and from the left being equals to infinity, and minus infinity here is similar from the left. Right? There must, for any m, no matter how small, the function must be less than m. Here I just described here, this approaches minus infinity from the left, and it approaches plus infinity from the right. The negative of this function approaches infinity from the left and minus infinity from the right. Okay. What we're also going to want to do is to look at functions as x gets very large. Right? The limit as x approaches infinity of f of x will be said to be a number L if given epsilon greater than 0, there is a number n so that f of x minus L is less than epsilon when x is larger than n. So that here, for example, the function 1 over x approaches 0 as x approaches infinity. Given any epsilon, if we want the function to stay between 0 plus or minus epsilon, we need to choose a number n out here, and it will. It will stay in this region here. The limit as x approaches minus infinity of f of x is L if, given epsilon greater than 0, there is an n, so that f of x minus L is an absolute value that's less than epsilon when x is less than n. So this function 1 over x approaches 0 as x approaches minus infinity, because if you want it to be within epsilon of 0, you need simply to choose an n, negative in this case, and whenever x is less than that n, then f of x will be within epsilon of 0. All right. Up here, if the limit as x approaches a from the right of f is plus infinity, and also from the left is plus infinity, then the limit is plus infinity. And similarly, if the limit from the right is minus infinity, and the limit from the left is minus infinity, then the limit is going to be infinity. The limit is defined to be infinity if, when you put absolute values in here, and that will clearly hold true if the limit from the right is infinity and the limit from the left is also infinity. Right. Furthermore now, if function f of x has a limit from the right or from the left of either plus or minus infinity, then as you get close to that point, either from the right or from the left, the function gets close to the line x equals a. And the line x equals a is called an asymptote. Okay? In this case here, it's called a horizontal asymptote. Right? If the limit is as x approaches infinity of f of x is L, then the line y equals L is also called an asymptote. The function gets close to that line as x gets close to infinity, and in this case it's called a vertical asymptote. Here, x equals a is a horizontal asymptote. Here the line y equals L is a vertical asymptote. In plotting the graph of functions, it's worthwhile knowing where you've got asymptotes or what happens to the function at a point if it's not near a point on the right and on the left if it's not defined at that point. All right. In addition to there being a finite limit as x approaches infinity, a good number of functions get very large in either positive or negative direction as x approaches infinity. So we want to also look at, in general, what happens as x approaches infinity of f of x. We want to say that this limit as x approaches infinity of f of x is equal to infinity if, for each number m greater than 0, there is an n. Well, actually, we don't have to have m greater than 0. Any number m, there is an n, so that f of x is larger than m when x is larger than n. Graphically, this will mean that the function is going off to larger and larger values as x gets large. And if we wish to make the values larger than m, we need simply find an appropriately large number n here, and they will be. That's to say, the graph of the function will be in that upper corner, so to speak, of the plane. Right? Then there are analogous definitions here. The limit as x approaches infinity of f of x will be minus infinity if for each m there is an n so that f of x is less than m when x is larger than n. Right? That's to say, for each number m here, now you can think of m as being negative. There has to be an n so that the function is less than m when x is larger than n. Right? And then similarly for the left-hand side. That's to say, the limit as x approaches minus infinity of f of x will be infinity if for each m there is an n. So f of x is larger than m when x is less than n. Right? Picture there, we'll have the function going up toward the so-called upper left-hand corner. Of course, there is no upper left-hand corner. Right? And the limit, finally, as x approaches minus infinity of f of x is equal to minus infinity if for each m there is an n so that f of x is less than m when x is less than n. So if we take a negative m here, we must be able to find an n, most likely negative, so that the function is less than m when x is less than n. So we have these definitions here, and it's always worthwhile to check a function to see what the limit is, if there is one, as x approaches plus infinity and as x approaches minus infinity. Now we want to take a look at a few types of the limits of functions as x approaches infinity. In particular, we want to look at polynomials and rational functions. And I'm going to explain the general theory of what happens to these by some examples. Let's suppose we take a look at, first of all, let's say f of x equals to x to the fifth minus 3,000 x to the fourth plus 10. And we want to look at the limit as x approaches infinity of f of x. Well, if you start plotting the graph of this, clearly, for example, when x is equal to 1, the graph's going to be somewhere around minus 3,000, and it looks like as if it's very negative. But it's also clear that when x gets to be as large as 3,000, the x to the fifth term is going to dominate the picture here, and we're going to have 3,000 to the fifth minus 3,000 to the fifth plus 10. Right? And when x gets very large here, the x to the fifth term is going to dominate the x to the fourth term, and it won't actually dominate any lower terms. So if this was 10x cubed minus 7x squared plus 1, let's say, these terms here, including the x to the fourth term, are not going to be the determining factor here in finding what happens to f of x. And the limit as x approaches infinity of this particular f of x is going to be equal to infinity, and the limit as x approaches minus infinity of f of x here, since x to the fifth is negative. When x is negative, the limit is going to be minus infinity as x approaches minus infinity. So the situation with respect to polynomials is this. The limit as x approaches infinity of a particular polynomial is the same as the limit of the so-called dominant term. That's to say the power of x, which is largest, and multiplied by its coefficients. Right? So that if this was a minus 3x to the fifth, then this would be minus infinity. Right? And this would be plus infinity. So it's the largest power of x which determines the limit when you're dealing with polynomials. Right? We now want to look at rational functions, that's to say the ratio of two polynomials. And again, I'm going to show what happens here by example. Let's take a look at the limit as x approaches infinity of 3x to the fourth, let's make it 3x to the fifth, minus 2x to the fourth plus 7 over 2x to the fifth plus 3x squared plus 8 as an example here. All right. Now, clearly the numerator approaches infinity, the denominator approaches infinity. It's not clear as a consequence what happens. But you can always determine what happens to a particular rational function by taking the highest power of x and dividing the numerator and denominator by it. So this is going to be equal to the limit as x approaches infinity of 3 minus 2 over x plus 7 over x to the fifth divided by 2 plus 3 over x cubed plus 8 over x to the fifth. And now, as x approaches infinity, this is going to approach 0, this is going to approach 0, this is going to approach 0, and this is going to approach 0. And so the numerator is going to approach 3, and the denominator is going to approach 3. Right? The situation here with respect to limits at infinity is they behave in the same fashion that limits at a finite number do. That's to say the limit of the sum is the sum of the limits, limit of the product of the limits. Limit of the quotient is the quotient of limits, providing the denominator is not 0 or, of course, plus infinity. If they're both plus infinity, I mean if there's a finite limit, in this case the numerator is going to approach 3, the denominator is going to approach 2, and so that this limit is going to be equal to 3/2. And it's clear from this that, in general, you can note that if the numerator and the denominator have the same largest power, then the limit as x approaches infinity of numerator over denominator is going to be the ratio of those two powers. The ratio of the coefficients of those powers. In this case, 3 over 2. Likewise, the limit as x approaches minus infinity. For the very same reasoning here, as x approaches minus infinity, all the things that are circled here are going to approach 0, and the limit as x approaches minus infinity is going to be 3/2. So the ratio of the leading coefficients in the event that the exponent in the numerator and the exponent in the denominator, the largest ones, are equal, is the limit. Right? What happens if the exponent in the denominator is larger? Let's look at the limit as x approaches infinity of 3x to the fourth minus 2x cubed plus 7 over 2x to the fifth plus 3x squared plus 8. Well, using the same method here, dividing by the highest power of x, we get that the limit as x approaches infinity here is equal to the limit as x approaches infinity of 3 minus 2 over x plus 7 over x to the fourth. I'm sorry, I'm going to divide by x to the fifth. So it's going to be 3 over x minus 2 over x squared plus 7 over x to the fifth divided by 2 plus 3 over x cubed plus 8 over x to the fifth. Right? And now all of these terms are going to approach 0. This one, this one, this one, this one, and this one, as x either approaches infinity or minus infinity. So if the numerator is going to approach 0, the denominator is going to approach 2, and the resulting limit is going to be equal to 0. That's also going to hold true as x approaches minus infinity. Right? So if the largest power is in the denominator, but not in the numerator, then the limit is going to be 0 for the ratio of the two polynomials. Right? Let's look at the final situation here, where the highest power is in the numerator. Let's look at 3x to the fifth plus 2x cubed plus 7 over 2x to the fourth plus 3x squared plus 8. And the limit as x approaches infinity. Now, if we perform the same operation here, we're going to find that we're going to have 3. Well, we're going to have the limit as x approaches infinity. We're going to have 3 in the numerator here, and 2 other terms which approach 0. And in the denominator, we're going to have terms which approach 0, all of them, when we divide by x to the 5th. All right? So that the numerator is going to approach 3, and the denominator is going to approach 0. And the question then is, the ratio of the two is going to get very large. And so you expect some sort of infinity for an answer here. And plus or minus is going to be the situation, and it's going to depend on what happens here to the leading term in the polynomials. Right? The polynomial in the numerator here, because we've got x to the 5th, and we're looking at x approaching infinity, 3x to the 5th is going to approach infinity, and 2x to the 4th is also going to approach infinity, so that the numerator here is going to get very large and positive. The denominator is going to be large and positive, but the numerator is going to be much larger, and so the plus infinity is going to be the situation here. Right? As x approaches minus infinity, now the numerator is large but negative. It's large in absolute value but negative. The denominator, because we have an x to the 4th power here, is going to be large in absolute value but positive, and so we're going to get minus infinity here. If this were x cubed, then both the numerator would approach minus infinity, the denominator would approach minus infinity, the ratio would eventually be positive and large, and you would get plus infinity if this was a cubed rather than a 4th. Being 4th and the 5th, you get minus infinity. So in order to determine what happens to the ratio of two polynomials, you can inspect if the highest powers are the same in numerator and denominator. The limit is, you can do this by inspection or use the simple method here of dividing by x to the highest power. By inspection, you get that the limit is going to be the ratio of these coefficients. If the highest power is in the denominator, the limit is going to be 0, either at plus infinity or at minus infinity. Right? If the highest power is in the numerator, then the limit should be either plus infinity or minus infinity, depending upon what happens to the numerator and what happens to the denominator as x approaches the particular value of plus infinity or minus infinity. That's to say, as x gets large, or as x gets large in absolute value but negative. So these are some simple examples here that give you a whole range of functions and how to compute the limits as x approaches infinity or minus infinity. So we want to look then at an example of graphing a function which will illustrate all of these things. Now, a person should work a lot of these examples. However, here's a particular one. It takes quite a bit to get practice at them. Let's look at x minus 1 over x minus 3 quantity squared. And let's let this be f of x. Right? Then, if we're looking for the graph of this particular function, it's not defined when x is equal to 3. So we want to look at what happens near 3. As what happens is x approaches 3 from the right or from the left. As x approaches 3 from the right or from the left, the numerator here is going to be positive. The denominator is also going to be positive, so that plus infinity is the limit from the right, and plus infinity is the limit from the left. And so the graph looks something like this. Near x equals 3. Since this is a polynomial of degree 2 in the denominator, and this is a polynomial of degree 1 in the numerator, we have that the limit as x approaches infinity of f of x is equal to 0, and that this is also equal to the limit as x approaches minus infinity of f of x. so that the function is going to have 0 for a horizontal asymptote on both sides, and it's going to have a line y equals 3 for a vertical asymptote. Okay, we now wish to take the derivative of this function. The derivative is equal to the denominator and the derivative of the numerator minus the numerator and the derivative of the denominator over the denominator squared. Now, here I'm going to keep the x minus 3 to the 4th power in the denominator here and rewrite this as factoring x minus 3 out of the numerator, x minus 3 times x minus 3 minus 2x on what? Plus 2. Or x minus 3 cubed now in the denominator, and in the numerator we've got minus x minus 1. Right? So this is going to be equal to 0, this right here, minus x minus 1. So this is going to be equal to 0 when x is equal to minus 1. So the derivative is going to be 0 right here. Now, we know the derivative is 0 here, and the function is not defined here. So if we check the derivative in between minus 1, the value of the function in minus 1 incidentally is what? Minus 2 over 16. So the function is small here at minus 1, but positive. I'm sorry, but negative, minus 2 over 16. All right. If we check now the derivative here at values to the left of minus 1, what happens? We have x minus, if we treat it in this form here, x minus 3 to the 4th and x minus 3 times this, the denominator will be positive. If we look at this at minus 10, this will be negative, and this will be positive, and so the derivative will be negative over here, and the function will be decreasing here until you get to minus 1. All right? How about between minus 1 and 3? For example, the derivative at 0 is minus 1 over minus 3 cubed, so it's positive. So the function is increasing here then between minus 1 and 3. Right? We can draw the graph something like this at this point. The function is 0 at 1, so that's an easy point to plot. And then the function has an asymptote like so. So the function looks something like this. How about the right of 3? Well, when x is larger than 3, for example, let's say at 10, the denominator is going to be positive, the numerator is going to be negative, so the function is going to be decreasing. We already know that it has an asymptote of 0, right? And we can also observe that it is going to be positive when x is larger than 1. Let's plot a point, let's say, for example, 4. At 4, we're going to be looking at 3 over 1. So the value of the function is 3 at 4. How about at 5? At 5, we're going to be looking at 4 over 4, so it's 1 here. And it clearly gets smaller after that. And so the function looks something like this. Right. Now, I drew this in without really checking the concavity. I expect that this is going to change concavity here. That's to say there's going to be an inflection point over here somewhere. This is going to be concave down, then up, and down and up also over on the right side of y equals 3. Let's check the second derivative. Here's the first derivative. The second derivative is equal to the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator three times x minus 3 squared over the denominator squared, x minus 3 to the 6th. All right? We want to simplify this. What I'm going to do is divide the x minus 3 squared out so that I've got x minus 3 to the 4th in the denominator. All right. And then what else have I got? I've got minus x minus 3. So minus x plus 3. And then the x minus 3 squared is divided out so that I've got minus 3 times minus x, so plus 3x. And I have minus a minus 3, so this is plus 3. So this is equals to 3x minus x is 2x and plus 6 over x plus 3 to the 4th, which is equal to 0 when x is minus 3. This should be x minus 3 to the 4th. Which is equal to 0 when x is minus 3. So that minus 3 is a place where the second derivative is 0. It's also clearly going to be positive when x is larger than minus 3 and negative when x is less than minus 3. So here's minus 3. This point right here is going to be an inflection point, and the function is going to be concave down over here, then it's concave up here, and it's concave up over here. And the value at the inflection point, minus 3, f of minus 3 is minus 4 over minus 6 squared over 36. So it's 1/9. This is an inflection point, and we discovered that minus 1 and minus 2 over 16, or 1/8. The point minus 1 minus 1/8 is the minimum, relative minimum. So there's an inflection point, and there's the relative minimum. All right. A couple things to note here. One is that if you've got something in factored form, it's a good idea not to multiply it out. You may find it difficult to refactor. Another one is that if you're dealing with a quotient and you want to know when it's greater than or equal to 0, you can determine when it's equal to 0 by checking the numerator. And then you can determine when it's greater than or equal to 0 by checking in between the points where the numerator is 0 and also the points where the function is not defined because perhaps the denominator is 0. If you check the various intervals, if the derivative is continuous, for example, you check in between those points. Here's a simple example, or not particularly simple example, actually it illustrates a number of things. Okay, let's take a look at another example. Graphing here. Let's say f of x is 1 over x minus 1 times x minus 3. Okay, let's take a look at what this function is going to look like. It's not defined when x is 1 or when x is 3, and because of the denominator approaching 0 there, you expect asymptotes. So the limit as x approaches 3 from the right, let's say. Well, when x is larger than 3, this is positive, and so is this. It's going to approach 0, and so this is going to be infinity, plus infinity. Right? So we can draw this in here like so. The limit as x approaches 3 from the left this is going to be negative, and this is going to be positive as x approaches 3 from the left, so that this limit is going to be minus infinity. So we can draw this in here like this. How about the limit as x approaches 1 from the right? Well, this is again going to be positive, and this is going to be negative, and so that the limit as x approaches 1 from the right of f of x is again going to be minus infinity, so that we can draw this like this. And the limit as x approaches 1 from the left of f of x, both of these are going to be negative, so the product is going to be positive, and so this is going to be infinity. The denominator is going to 0, and so we get this picture right here like so. As x approaches infinity, the function approaches 0, and likewise as x approaches minus infinity, the function approaches 0. So 0 is an asymptote for the function like so. I'm going to draw it in like this, presuming that the function is positive, which apparently it is when x is larger than 3, and it's also positive when x is less than minus 1. So we don't have to put anything in the graph here or here. All right. The derivative. The derivative is the denominator times the derivative of the numerator, 0, minus the numerator times the derivative of the denominator. So that's the first times the derivative of the second, plus the second times the derivative of the first, over the denominator squared. So this is going to be equal to, what have we got here? 2x minus 2. Oh, this should be x minus 3. 2x minus 4. So we have minus 2x plus 4 over x minus 1 squared times x minus 3 squared. And that's equal to 0. When x is 2. And that's the only place where it's equal to 0. Let's look at the function 2. This is 1 and minus 1, so the function at 2 is minus 1, and looks like this. All right. I'm going to draw this in at this point here. Because what? The denominator in the derivative is positive. The derivative is positive when x is, so it's greater than 0, when x is less than 2. So well, of course, it's not defined when x is minus 1, but that's what that says, is that this function has to be increasing here and increasing here. Let's plot the point at 0. All right, the value at 0 is a third. So it's like so. And so we can draw this more or less like this. The function is increasing. And like this. And now, when x, this is going to be less than 0 when x is greater than 2. Let's plot also the value of the function at 4. The value of the function at 4, this is 1, and this is 3, so it's also a third here. You can actually show here that this function is symmetric about this point, 2. The function is decreasing now over here. I'm drawing it more or less like this. I'm also presuming that the concavity is as I've drawn it. And while I'm going to compute the second derivative of this function, I think this is going to be one of those instances where the second derivative is a little bit difficult to deal with because it's a bit on the messy side. Let's take a look at it. The second derivative. Right? Well, it's equal to the denominator times the derivative of the numerator, which is minus 2, minus the numerator times the derivative of the denominator over the denominator squared. So this is x minus 1 to the 4th times x minus 3 to the 4th. And now we need the derivative of the denominator here. And so that's the first, x minus 1 squared times the derivative of the second, 2 times x minus 3, plus the second, x minus 3 squared times the derivative of the first, 2 times x minus 1. Okay, so this is the second derivative. Now, this will simplify some. And I believe that you can, if you do simplify it, that you can show that the second derivative is never 0, and that it is positive here, and negative here, and positive here, so that you get the concavity that I've drawn. But this is an instance where the second derivative is not particularly neat, and it's best, perhaps, unless you want to go to a lot of work, to rely on the information that you get from the limits and the first derivative. Let's take a look at another example. This is an example of a function that occurs with some regularity. F of x equal to 1 over 1 plus x squared. Right. The function is always positive. It's defined for all x. And what? When x is equal to 0, it's equal to 1. It's also symmetric about the y-axis. And the limit as x approaches infinity is going to be 0. Also minus infinity here. It's going to be 0. All right. Let's take a look at the derivative. Denominator times the derivative of the numerator minus the 0 times the minus the numerator times the derivative of the denominator over the denominator squared. Okay, this is no real surprise here. It's equal to 0 when x is 0, and it's negative when x is greater than 0, and it's positive when x is less than 0. So the function is decreasing here like so. That's really very intuitive from the fact that as x gets large, starting from 0, the function gets smaller, and like so. Right. Now, we expect here that it can't just do this without having an inflection point somewhere in here. And so let's take a look at the second derivative. This is going to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which is 2 times 1 plus x squared to the first times 2x over the denominator squared. 1 plus x squared to the 4th power. Now we can cancel a 1 plus x squared with the 1 in the denominator here. Dividing 1 plus x squared out, we're going to get 1 plus x squared cubed down here, and we're going to get minus 2 times 1 plus x squared, so minus 2 minus x squared, and plus 8x squared. And so when is this equal to 0? Well, when the numerator is, and that's to say when minus 2 this should be, what, minus 2 times minus 2x squared plus 8x squared. So when minus 2, we end up with 6x squared plus 6x squared is 0. That's to say when 6x squared is 2, what x squared is equal to 3, or what x is equal to plus or minus the square root of 3 is when this is 0. So if this is 1, at the plus or minus the square root of 3, there's going to be a deflection point. And so the function is going to be concave up here, concave down, and then concave up. Okay. So there's that function. Let's take a look at one more example here then of graphing a function. Let's look at x minus the square root x squared plus 1, f of x. Okay, the function is defined for all x. The question is, what does the graph look like? What happens when x gets large here? Let's take a look at the limit as x approaches infinity of x minus the square root x squared plus 1. Well, as x gets large, this gets large, and this gets large also, and you can't tell here. And, well, you need to use a standard trick by this time, perhaps. Multiply and divide by x plus the square root x squared plus 1. Treat this as a minus b and multiply by a plus b and then divide by it. Right. In which case we get that this is equal to the limit as x approaches infinity of x squared minus x squared minus 1. So minus 1 over x plus the square root x squared plus 1. And now as x gets very large, the denominator here gets large, and so that this approaches 0. How about the limit as x approaches minus infinity? Okay. What happens here? When x approaches minus infinity, this is negative, and so is this. And so the limit as x approaches minus infinity of f of x is going to be minus infinity. All right, well, let's look at a point to plot here. A simple point would be perhaps 0, for example, where the function is minus 1. All right. At this point, you might suspect this function is never positive. The question is, see, it's going to have an asymptote of 0 here, and it's going to approach minus infinity down here. Does this function ever become positive? Well, let's see, when is the function equal to 0? Well, it's going to be equal to 0 when x is equal to the square root x squared is equal to x squared plus 1, or 1 is equal to 0, so it's never equal to f of x is never equal to 0. Right? So the function is not defined, it does not take on its values up here, and perhaps it looks something like this. Perhaps more complicated, but perhaps something like this. Let's look at the derivative. Right? F prime of x is 1 minus 1/2 x squared plus 1 to the minus 1/2, which is going to be equals to L times 2x, which is going to be equals to the 2 and the half will cancel here, and I'm going to get x over the square root of x squared plus 1. All right, and now I've got the square root of x squared plus 1. If I put this 1 over the square root of x squared plus 1, so I'll have the square root of x squared plus 1 plus x minus x. Right? Now we already determined that x minus x squared plus 1 is always negative, so square root x squared plus 1 minus x is always going to be positive, so that says that the function is strictly increasing. Right? Suggesting something like this. Let's take a look at the concavity then. What is this? The second derivative? Derivative of 1 is 0. I'm going to treat this as if these are canceled here. So this is a product. It's minus x times x squared plus 1 to the minus 1/2. So the derivative is going to be minus 1/2 x squared plus 1 to the minus 3/2. That's the first minus x times the derivative of the second, plus the second minus x squared plus 1 to the minus 1/2 times the derivative of the first, which is 1. So let's put this over the common denominator, x squared plus 1 to the 3/2. I suppose we should check it here first of all. It's 2. What? It's the first minus x times the derivative of the second. Minus 1/2 x squared plus 1 to the minus 3/2 times 2x. Plus the second, x squared plus 1 to the minus 1/2 times the derivative of minus x, which is 1. Okay, so we missed the 2x term here. All right. If we put this over a common denominator here, what have we got? We've got 2x times minus 1/2 times x times minus x is going to give us x squared. And then we've got minus x squared plus 1. So minus x squared minus 1. So that the derivative is equal to minus 1 over x squared plus 1 to the 3/2 power. The derivative is always negative, and so consequently the function is always concave down. This is always less than 0. The function is concave down and increasing, and so the graph looks like so.